Kia ora and welcome to video 17 in the series Delightful Differentiation. This problem here is fairly straightforward. We need to find the nth derivative of that function. Just be sure that you do some simplification after your first derivative to ensure that the second, third and subsequent derivatives don't become a mess to handle. We need to prove that the nth derivative equals this expression. It's okay just to reason as to why there is a pattern in the derivatives and why that pattern is the one that you're given there. Good luck with the problem, and we'll catch you for the solution shortly. Okay, so this problem requires us to find the nth derivative of this function p of x. And I just want to put it straight out there and say that if you're proving something to do with natural numbers, there is this process called mathematical induction. This video is not going to cover that. But mathematical induction is a process where if you can prove that it works, some proposition works for a base case. So in other words, we could prove that this works for n equals 1 and say, hey, the first derivative, the formula matches. And then we assume it works for some step along the way. So something like n is equal to k. We say, okay, let's assume that it works. And then we differentiate it one more time to the k plus 1 term. And if we can prove that works, that the formula matches, then we can go all the way back to our base case and say, well, 1 works, therefore 2 works, 2 works, therefore 3 works, and so on. So this can be proven using mathematical induction, but I don't think that's assumed that you're aware of that if you're doing scholarship calculus. So we're just going to establish a pattern by differentiating this a number of times to see that there's a periodic sort of nature. It repeats, it starts to repeat itself. Okay, so the first derivative, we're just going to use chain rule to find that. P of x is equal to sine x all to the 4 plus cos x all to the 4. P dash, the first derivative, 4 sine x cubed, so I'll just start writing with the 3 in the inside, looks a lot tidier, times the derivative of sine, which is cosine, and then similarly, 4 comes down the front, cos cubed multiplied by the derivative of cosine, which is minus sine. Okay, so that's our first derivative. And we're going to tidy this up before we move on because we need to establish an expression for the nth derivative. And if we're going to get to a first derivative that's a messy product, it's just going to blow up. So let's tidy this up a little bit by first recognizing that there are some common factors here. Both terms have a sine and a cosine, or at least one of, and they've got a factor of 4. So if we factor out 4 sine x cosine x out of both terms, then we end up with sine squared x there, and we end up with minus cosine squared x there. Okay, we could tidy this up even further. Sine squared minus cosine squared is on the double angle formula. So on the formula sheet, down in the double angles, it's minus cos 2x. And sine x cosine x is similar to the double angle for sine. I should actually rewrite these down. But on the formula sheet, it says cos 2x equals cos squared x minus sine squared x. Okay, so be careful, it's a minus, not a plus. If it was a plus, it would be 1. And there's also sine 2x is equal to 2 sine x cos x. So that are the identities that I'm using here to rewrite my first derivative in a simpler format. We have 4 sine x cosine x, that's 2 lots of sine 2x. We have a minus coming out of the second term, so we've got minus 2 sine 2x cos 2x. Now that's double angle formula again, except that the angle here is 2x, which means that we can write this as minus sine 4x. Why have I bothered to do all that? If we look at what we're trying to prove, the expression has a 4x term in it. And we started off with a first derivative that only had x's in it, so I've turned it into an expression that's got 4x's in it. Okay, so does the formula actually work for n equals 1? That is the question. When n is equal to 1, p dash of x, that dash looks like a 1, first derivative. When n is equal to 1, we're going to get 4 to the 0 times cosine of 4x. Yeah, cosine 4x. We got minus sine 4x. What's gone wrong? My bad. N is equal to 1, so we actually need to add a pi over 2 in there. Okay, now when we add a pi over 2 to a cosine graph, if you think about what a cosine graph looks like, it doesn't matter about the fact that it's got a 4x in it. It's cosine of something. When we add pi over 2 in the inside of those brackets, it has the effect of moving something to the left by pi over 2. So if we move this to the left by pi over 2, it would look like that, which is a negative sine graph because it's starting at the origin. That's pi over 2 and moving its way downwards. Okay, so yes, that does equal negative sine of 4x. Cool. Now we're in this relatively simple expression for things. We can differentiate again without having to worry about messy products or trig identities. P dash dash x, the second derivative, sine goes to cosine, but this is minus sine, so we're going to go to minus 4 cosine of 4x. And then third derivative, just so we can establish this periodic thing, cosine goes to minus sine. We've got minus 4 in the front there, so we're going to get to 16 sine of 4x. And then lastly, the fourth derivative, I can't be bothered writing 4 dashes, so we'll switch to the other notation. Sine goes to cosine, we've got 64 cosine of 4x. So in the front, the coefficient there in the front is going up in powers of 4, which is definitely related to that there. The n minus 1 comes from the fact that the first derivative actually didn't have a 4. And then the cosine of 4x plus n pi over 2 thing. So as we're moving our way down this, we're going from a negative sine graph to a negative cosine. Then we're going from a negative cosine to a positive sine. Then we're going from a positive sine to a positive cosine, and so on. So there's we're kind of generalizing here. But to be a bit more convincing, we need to bring in this, all of them need to be written as a cosine. Okay. So the first one, negative sine of 4x, I need to write that as 4 to the 0 cosine of 4x plus pi over 2. As explained before, when we take a cosine and we put a plus pi over 2 in it, we're moving it to the left, turning it into a minus sign. This next one here, negative 4, we'll worry about that in a sec. It's an upside down cosine graph. An upside down cosine graph relates to a positive cosine graph. It's just out by half its period. So 4x plus pi, which is 2 pi over 2. The next one here is 4 squared. 16 is 4 squared. A sine graph, a positive sine graph, is out by 3 pi over 2. So it's 4x plus 3 pi over 2. And lastly, we're back to a positive cosine graph. So it's 4 to the power of 3 cosine 4x. Of course, I could write it as cosine 4x, but if I add 2 pi in here, it does nothing to the graph. So cosine of 4x plus 2 pi, and then we can establish the fact that this is just n pi over 2. So in general, whilst not really a proof, we've established the periodic nature of it and the fact that when we differentiate sine, we get back to sine 4 derivatives later. Okay, 4 to the n minus 1 cos 4x plus n. It's not a funny looking n pi over 2. Happy days.